All right. Good afternoon, guys. Today we want to continue with our lesson on waves. Okay, and we want to look at wave fronts today. Wave fronts. So our lesson will be quite short today. Yeah. So first of all, we'd want to look at what a wave front is. Okay. So a wave front is basically a line that is taken through an advancing wave in which all the particles are in the same phase. I'm repeating that. I'm saying that a wavefront is basically a line, and this line is taken through an advancing wave in which all the particles are in the same phase. Okay, so a line at right angle to a wavefront which allows its direction of travel, or which shows its direction of travel, is said to be a ray. I'm saying that a line at right angles to a wave, or a line at right angles to a wavefront which shows its direction of travel, is called a ray. So here basically we are permitted at your level to look at two types of waves or wavefronts. We're looking at two types of wavefronts. So number one, we are looking at the plane wavefront, and number two, the spherical wavefront. All right, so let's look at them simultaneously. Let's begin with the plane wavefront. All right, so let's consider this diagram with respect to a plane wavefront. Okay, say we have um, a plane wavefront to be demonstrated from this diagram. Here we have a line source. Okay, so that is our line source. So we have our line source, and then we can see that a line is drawn perpendicularly to the line source. So that horizontal line we are seeing drawn like that is a ray. So this is what we're calling a ray per our definition. Okay, so at this point, let's consider a plane wavefront produced at say A and B. All right, and then let's have succession of them. So let's say this is a plane wave front. All right. So basically, we are saying that if a line source is periodic, as we see in the diagram, if that line source in our diagram is periodic, then a plane wave is produced, and this creates a wavefront that are straight in two dimensions, or or cylindrical in three dimensions. Okay, so we are going to say that if a line source is periodic, the plane wave that is produced creates a wavefront. Okay, and the wavefront is either straight when in two dimensions. So in two dimensions, our wavefront looks straight. Okay, but in let's say in a cylindrical dimension, in a cylindrical dimension then our wavefront wouldn't look straight. Okay, it would in two dimensions the wavefront created will look straight, but in a cylindrical dimension it will mean that it will appear cylindrical. when a wavefront is studied in three dimensions. So let me just say and reframe this sentence here. So in three dimensions, a wavefront would appear cylindrical, but in yeah, let me put it this way. Yeah. So in two dimension, our wavefront appears straight. Okay, so you can see that it appears straight line, straight line, straight line, straight line. And all these straight wave fronts, called the plane wave fronts, are perpendicular to the ray that is directed from the line source. Okay, so in two dimensions, a plane wave front appears in a straight line, but in three dimensions, our wave front would appear cylindrical. Okay, so following that, an example of a line source is a straight vibrator on the surface of water. All right, so this represents a series of, or this, yeah, this represents a series of plane surfaces. For instance, this surface AB is reproduced in a series, as we can see in the diagram, and it's because of the vibrations produced by the vibrator. Okay, and this line AB, as we are seeing as the plane wavefront, is also parallel to each other. Right, now let us consider the spherical or circular wavefront. All right, we're looking at the spherical or circular wavefront. So say we have a point source. So here we have a point, and that point here is our point source. Okay. All right. So note that with the plane wavefront, we were dealing with a line source. Now with the circular or spherical wavefront, we are dealing with a point source. So let's assume that there's a point source, and this point source is periodic. All right. So a circular or spherical wave is produced as it consists of a succession of circular wavefronts. So in two dimensions, and then also spherical wavefronts in three dimensions. So in two dimensions, this produces successions of circular wavefronts. And then in three dimensions, this will produce a succession of spherical wavefronts. All right, so this is basically what I just said. So in two dimensions, circular wavefronts are produced by a point source. And then in three dimensions, spherical wavefronts are produced by the point source. Okay, so you can see that here the ray is also directed perpendicular to the point source. All right, so that becomes a circular wave front. Okay, so I believe the differences are spelled out clear. A line source is a source for a plane wavefront, and then a point source is a source for a spherical or circular wavefront. So now let's look at the phase of a wave. All right, so the phase of a wave is basically the angle that is made by the vibrating particle with respect to the equilibrium position. I'm taking it again. I'm saying that the phase of a wave is the angle made by the vibrating particle with respect to the equilibrium position. So here, let's consider um, this as we have here. Okay, so let's consider this diagram. All right, so let's say that is x, y, p. Let's say that is y prime, that is x prime. All right, so what we're trying to say is let's consider the particle p. Okay, so this particle p is moving in a circle of radius a. All right, so it's moving the circle of radius a. So radius is equal to a. All right, and then this a represents the amplitude of the wave with an angular velocity omega. All right, so uh, they have the radius a, which is the amplitude of the wave with an angular velocity omega. So at this point, we are having this angle here as a phase angle. Now, at P, okay, so at the point P, the phase angle, which is phi, this phi symbol represents our phase angle or our phase. So at P, the phase, which is phi, at the point Y, at the point Y, the phase is pi over 2. So at the point Y, the phase is 1 over 2. So all we're trying to say is at Y. So at Y, our phi is equal to pi over 2. Okay, so at Y, this is pi over 2. And this goes a long way to explain that two particles in a wave are in phase when they are at exactly the same displacement in their paths and are moving in the same direction. I'm taking it again. I'm saying that two particles in a wave are in phase when they are at exactly the same displacement in their paths and are moving in the same direction. So thank you so much. We're going to end this lesson right here and we will proceed with the classification of waves when we meet during another or our other video lesson. See you all. Bye bye.